So thanks to organizers for this opportunity, and thanks for also solving the technical problems. Well done. So 12 points from Helsinki go to the organizers. So I'm not presenting any actual results, but more like some ideas of what might be done by combining the already existing tools and techniques with some available data, and trying to assess both the microbiological and chemical risks. So to compare both of them, so can we use the bottom-up approach for both? So that would be calculating from the exposures to population effect, so the whole pathway from cause to effect. And so as we know, for chemical hazards, the story goes like mostly about chronic effects. And then in this case, I'm just thinking about binary effects, something like yes, no. And basically, these are the kind of lifetime effects. But there are several effects, as have been shown in the previous presentations, and they can have different severities. So all of this needs some exposure estimation, of course, to get to the exposure estimates of this. And so we are assuming that there's some foodborne food diary data for estimating the exposures, and that means also concentration data from the same foods. And usually, in this case, we would have dose response data from animal studies, and also that in these cases, there's usually some non-zero baseline risk also in those dose response models. But then looking at the microbiological side, then the story is about usually acute effects, and then you can have several illnesses in a lifetime. And the effect usually of interest is the illness. So basically, we are usually interested in one effect, the illness, gastrointestinal illness. But in the same way, we need the same kind of data for exposure estimation. Again, some food diary data and concentration data from those foods for the hazards. But usually, in microbiological side, the dose response model could be directly from human studies, could be experimental, could be outbreak data or something like that. And all of these kind of topics actually were discussed a bit in the previous risk ranking project that you might know of. So the link is here. So that was the one we had with the Swedish colleagues. And so in that, we were already discussing the kind of commonalities and differences between microbiological and chemical hazards and how they might be compared. So apart from those things that we can actually estimate, there are always some unknown things that are difficult to quantify. And maybe one difficulty is for the chemical hazards is to have the animal dose response, and then what is the human equivalent dose? How do we get the human dose response from animal dose response data? And there are different ideas and techniques also for that. For example, some allometric factors to convert the doses so that they would be somehow possible to calculate for humans, even when you have this animal dose response data, and then to make the conversion. There's a lot of modeling issues and things behind this, but for this 15 minutes, I make everything very simple and straightforward. So I'm assuming that there is some way to convert the kind of human equivalent dose from the animal studies. And likewise, very difficult thing in the microbiological side is to actually estimate the actual dose at the time of consumption, because usually we have the data from some earlier step of the food chain. So there could be concentration data from the market or the industry or from the raw meat products, but then you have to take into account the bacteria growth or inactivation that happens before the actual consumption, and this might be difficult to quantify. But again, I'm assuming that there's some way of doing this and some knowledge that makes it possible to use some growth models and then to translate the actual measurements we have to some predictions of what they could be at the time of consumption. So just to make things very simple in this presentation. And even further simplification for chemical hazards, because there can be a very large number of effects. So we have actually a large number of dose response functions, and these could be grouped and combined into fewer ones by grouping them according to the severities. So it would be possible to calculate actually the dose response functions for different severity categories instead of each individual effect. So that kind of simplification then could help in somehow grouping them into a smaller number of things to quantify. And because of these effects are chronic effects, so thinking about the human effects, a lifetime effect, lifetime could be 80 years, but we could also translate these lifetime effects into annual risk by dividing by the number of assumed life years. And assuming also that there's only one chronic illness in your lifetime. So if you get one cancer, then that's the one you get. And then looking at the microbiological side, again, a lifetime of the same duration is quite many days. And then because microbiological hazards happen as acute single events, so you can have multiple infections in a lifetime. And so basically every day when you eat something is a possibility to get a gastrointestinal illness or infection. And then basically to make this comparable, we could try to integrate and the cumulative number of cases that could happen in a longer time. So, and all of this was actually discussed in this paper by Lindqvist et al. So we were trying to compare both these chemical and microbiological assessments in a common approach in this paper, and so you might take a look at that. So about quantifying the uncertainties that can be quantified. So basically, we can derive parameter uncertainty distributions as posterior distributions from the dose response data. So in this picture shows what it might look like for one chemical hazard that has several different possible effects. And so there's one dose response function for each of those effects. And you see that, okay, those clouds of points just describe the uncertainty distribution of the parameters. So you can see that some parameters for some of those effects become estimated more accurately than others. So there's a big difference in the amount of uncertainty that we have based on the data. And this uncertainty could be reflected in the final estimates. And you also see that some of them, these effects, they have already quite high baseline risk, which means that it might not be so big effect to change or control the dose, because if the baseline effect is already very high, then it's not so much depending on the exposure that you can control from the food, for example, if the baseline risk is already high. But for some of those, it's not the case. And for the microbiological hazards, there can be several different bacteria strains, and we can have dose response data for each bacteria strain. And you see that some of those strains and the dose responses again can be more accurately estimated than others. So there's again big difference in the uncertainties for some of the bacteria strains about what kind of dose response there possibly could be. But here we have the same effect, the illness or infection. And here, for example, in this picture, it could be comparing Campylobacter and Salmonella, estimation of the dose response parameters and the uncertainties about those. And so all of these uncertainties, these things can be calculated by using these existing estimation methods, and this can be translated into uncertainties of the dose response functions. So in the chemical side, you would have dose response functions and the associated uncertainties for them for different severity categories when they are now grouped into these categories instead of all of those individual effects. And for the microbiological side, you could have like here dose response functions for let's say Campylobacter and Salmonella, and then in this picture you basically see that not every infection leads to illness. So that's one difference also for the microbiological side, that even when you increase the dose, then still not everybody gets ill. And then finally combining the exposure estimation with the dose response functions, this might be combined into this kind of comparison tool that basically allows you to control some of those difficult parameters by using some expert opinions or assumptions about them or kind of scenarios. And then these exposure distributions could be coming from some existing models, because we have actually quite many exposure models that can be used, and we have been also developing one that can be used for deriving exposure distributions for microbiological and chemical hazards. So those tools can be used for obtaining those kind of exposure distributions, both for chemicals and microbiological things, and then combining them with these dose response models and the associated uncertainties in them, and then noting here again that not all infections lead to illness, and then integrating all of this together gives you some uncertainty estimation for the number of cases of each type that could happen in a population per 100,000 people in a lifetime. And so basically that would be a quantification of the preventable cases that could be prevented if you could push the dose towards zero. So how many cases could be reduced? And then you have some uncertainty limits that come from the uncertainties of the dose responses and the uncertainties and variability of the exposures. And then you can play with some scenarios and expert opinions and assumptions that maybe in the default case you could calculate it like this, that assume that human dose response equals the animal dose response, and assuming for the microbiological side that there's no growth or inactivation that from those measurements that you put in the model, and then you calculate some output, how many cases of illness you then would get and how many number of cases of different severities you might get in numbers per 100,000 people. And then you could play with these assumptions that assuming that humans would be 10 times more sensitive than the animals in the dose response experiments, and then you get a different number of cases, and then assuming that humans are 50 times more sensitive, then you get again different amounts and different uncertainties. And for the microbiological side, you could play with some assumptions that what happens if you increase the variance of the contamination of the CFU in the microbiological hazards, then increasing the variation will actually increase the number of high doses, and high doses mean more cases. And then you could experiment with this, that okay, how much effect this could have on the number of cases, or how much effect there would be by pushing the prevalence of the hazard down, and then you would have less contaminated servings, and then consequently less cases, and you could calculate this. And then you could also do some other scenarios by reducing the concentration of the microbiological hazards by -2 logarithms. So that would mean that there is better hygiene, and then of course you would then get again less cases, and you can play with these assumptions in this calculator, and so basically combine the quantifiable and unquantifiable uncertainties in these calculations. So quite many things can be actually quantified about the uncertainties. So we can quantify the parameter uncertainty by using modeling and simulations and using the existing data. And then the more data you get, then the less uncertainty you will have in the end, and you can reflect all of that in the consequent calculations And there are some important differences that's then accounted for in these calculations, that for some parameters and some hazards, you have much more uncertainty than for something else, which is important to have in the outputs. And then always there are some unknown factors that are very, very difficult to estimate, but you can assess these as scenarios or expert opinions, or try worst case and best case scenarios. And then these comparisons could actually in the end prove that some factor to be either completely unimportant or important, which depends on at what level of exposure we actually are at. So it might not be so important in the end that is the factor 10 times or 20 times bigger if the exposure is already so low that it doesn't have so much effect. But all of this contributes to the overall uncertainty. And of course, also the model choice is one issue that you can experiment by trying different models with different parameters, and then that concerns also the exposure models and the dose response models, and you can select and try different models and see how much actually this affects your conclusions. And by comparing different models, you can get an idea of how sensitive all of this is to the model choice. So the bottom-up approach, so the main challenges are, of course, in the inherent knowledge gaps along the causal pathways. So maybe a tiered approach could be one general approach that could be helpful to start with. And of course, one difficulty is the timescales, because in the acute microbiological things, they happen like on a daily basis. You either get ill or not. And in the chemical, it's a long process for a chronic illness. And then there's a question about competing or dependent risks, that how to model these, because one health condition could be a precondition for some other condition. And so the set of all possible effects may not be independent. So should they be counted in like some kind of a dependent set of effects that happen, that first something has to happen before something else can happen. So like gradually progressing a health condition, or in the microbiological side, you know that sigille requires illness, which requires infection. So it's actually a process of different effects going in a sequence, and not kind of independently. But then the top-down approach, that's a different story. So it could be worth to compare both approaches and to see that, okay, do you still get the same kind of output in the end if you do both the bottom-up and the top-down approach? But the top-down, that actually requires to have epidemiological registered data on reported cases. And as you know, there's a question about underreporting. And then it also would need epidemiological data about risk ratios for chemical effects for computing the population attributable fractions. And for microbiological things, it might need source attribution methods. So that's another type of difficulty in this approach. So, but in any case, in finally, you have then kind of ways to quantify these multiple types of effects, but then how to make the final comparison. It might need this multi-criteria decision analysis, or going for some common metrics such as DALIs, if those are applicable, to make some kind of final comparison of all of those. So that's just some vague ideas and possibilities. And so thank you.